another Legion meeting, or Legion brown bag session. So this week we're going to be doing some more control application stuff. I want to talk a little bit about how control application gets started, and then a few other important sort of aspects of control application. So actually, before I do that, let's jump back over here to the slides. So previously we've kind of like been jumping into the middle of control application and looking at, as we've dived into a lot of detail into how, control application does its analysis in the logical dependence analysis stage of the pipeline, how that stage is replicated across all the shards, and how they figure out dependencies between tasks that are launched, between the different shards, and make sure we add fences and stuff in the right places. So we've really done a deep dive into this stage of the pipeline. But what I want to do today is actually take a step back, talk about how control application gets started, talk a little bit about how some other operations, what happens when you get to like the mapping stage of the pipeline for control application, and then maybe look at replicated feature maps just as like the last sort of miscellaneous feature of control application, that we probably want to be aware of. So we've done deep dives for this, but we're going to start today with like how does control application even get started inside of the runtime. Right. So let's actually take a quick look. This is mostly just an interface for for thinking about how mappers decide to actually control a replicated task. Right. So the first thing that mappers can do to enable control application, right, is effectively in the select task options. There's this replicate flag right here. Right, that effectively allows mappers to say, I would like the option to potentially replicate this particular task, right? And that will effectively trigger an additional mapper call to talk about how to control replicate that task. If that's set to false, then the task is not going to be replicated. But if you set that to true, then you get an additional mapper callback from the runtime for this particular task to say how you want to control replicate it. Right, so if you set this to true, right, you see it's false by default, so it's off. Most tasks are not control replicated, but if you do opt into that, then you get an additional mapper callback, which is the map replicate task callback. And this is the callback that effectively asks you, how do you want to potentially replicate this particular task, right? I will say this interface is not completely set in stone. There's been some requests to change it before we finally merge control application, and so there might be some changes to this interface, but there will always be this map replicate task callback to effectively decide how to replicate a particular task into multiple copies of it. And the distinction between control application and normal replication really in Legion is just whether your task is going to use leaf task variants or normal inner task variants, which can launch subtasks and stuff like that. So if you say, you're only going to map, this task with a leaf task variant, then Legion doesn't need to do control application, it just does normal replication, right? Because like effectively, that leaf tasks aren't going to need to cooperate to launch subtasks and stuff themselves. So you can effectively just, normally replicate the task and have multiple copies of it run on different places. But if your task is not going to be a leaf task, it's actually going to be able to launch subtasks and stuff like that, then you have to do control application. And so Legion will handle that for you. Now, the way you make copies of a task is you effectively at least today, is you populate this task mappings vector, which you fill in like the map task output, structure for as many copies of this task as you want to make, and you'll assign those to processors, and each one of those will be effectively a shard of this task as it's being replicated, right? And of course, if your selected variants are not not leaf tasks, then we will end up doing control application for you in the background. And today you have to fill in this like control application map. I think this is actually optional, I think, at this point. Like we can actually fill out your control application map from your selected map task output today. Effectively, this is just saying, for each of the shards, this vector needs to be the same size as this vector, and says which processor each of your shards are going to be run on, right? So for as many copies of this task as you want to make, right, we'll run a shard on each of those different processors that you're assigning. And these two data structures down here are optional things that you can fill in. Effectively, you can specify like, normally, when you make shards, Legion will assign, each of your copies a shard ID, which is an unsigned integer from 0 to n-1, where n is the size of these two of this vector or this control application map, right? They need to be the same. That's the number of copies of the task you made, right? But you could also like give names to your shards, which are not unsigned integers, right? And you can use a domain of and some points to assign to give names to your shards if you want to, and that's useful for like the sharding functors. If you do provide like a non-one-dimensional thing, you can, or non-dimensional set of names of shards, then the sharding functor interface Legion will call back with the right names that you've assigned to each of the copies of the task that you've made here, right? So if you do fill this in, this vector needs to be the same size as these other two vectors up here, right? And that'll give a name to each one of those copies of the task, and this is the domain of all the points, right? And you don't have to fill these things in. These two here are optional. If you don't use them, then Legion will just assign shard IDs based on 0 to n-1 for each of the elements in each of these vectors, right? And that gives you names for these things. But effectively, this is how the mapper chooses to make copies of shards, right? The mapper decides how many shards to make and which processors they're going to run on and stuff like that. And then Legion is responsible for carrying out the wishes of the mapper, for control replicating this particular task, right? It's important to note here that you don't have to use often people will make copies of the top level task that make one shard for every node in the machine or something like that, right? You don't have to do that. You can have multiple shards on the same node. You could have shards just on some of the nodes, but not on other nodes, right? It's completely flexible here. The mapping interface, right? You can control replicate and make as many shards as you want for any given task that you're going to replicate. So the mapper can control all this stuff. Now, internally, the runtime has to actually carry out and create data structures to actually do the execution for each of these shards. So I wanted to show you today is sort of the architecture of what that looks like. So let me jump back down here. So this is kind of the important picture of how control application gets started. So you've got a single point task, individual task that you've decided to replicate, right? Make multiple copies of it, right? The mapper has said they want, this particular example, they said they wanted 6 shards, right? And they've assigned, processor names to each of those different shards to say where they're going to run, right? And so Legion has to create some data structures to help manage the execution of this of all those different shards and make them look like they're control replicated and that they're all cooperating together as one logical task, right? Effectively, we've replicated one task up here, but there'll be multiple copies of it, but they're all executing as one logical task. And so the data structures that we make for this, there are effectively 2 levels to the data structures, right? So the first one are these shard managers. And these shard managers effectively are going to be made for this control replicated task on each of the nodes where at least one shard exists, right? And let me show you where the shard manager class is in the code, just a couple of back. So if we look in Legion replication.h here, there's a shard manager class here, right? Which is effectively you can notice this is another one of the distributed collectible classes, right? Effectively, it knows about it's multiple copies of the same shard manager on different nodes, right? And what it's going to do is going to track the names of all of the replicated contexts for each of these shards, right? So the main data structure that we've got down here, or I guess the main thing to be realized is this vector of shard tasks here, right? Which effectively are going to be effectively the local shards that exist on this particular node, and there can be more than one of them, right? And you can see you can have imbalance here, right? You can have one shard manager that has 2 shards, another shard manager that only has 1 on its node, and so forth. So you don't need to have there's not necessarily any symmetry here between each of these different shard managers, right? But the one guarantee you do have is that for any given control replicated task, there's exactly one shard manager on each node where a shard exists. And you can have and they all share, and I should say, since these shard managers are all copies of the same thing, they're all distributed collectibles. Each of these shard managers has the same distributed ID, right? So you can effectively use that to jump from one node to another and find the shard manager on a different node using that same distributed ID. Okay, and so what happens is when you make this control replicated task, there's actually a broadcast process which will make all these shard managers. It actually does this broadcast as like a tree broadcast, right? Just launch out each of these shard managers. And then what these shard managers do is they actually make, effectively a shard task and a replicated context for each of the shards that they're going to run on their local node. And right, you can actually see that this, this vector of local shards here. Let's actually go take a look at that shard task class just to show you where that exists in the type system. Nope, I did not copy properly. Let's see. Let's copy this again, and we'll do Legion tasks.h. And if we look for the shard task class, right? So this is the shard task class that we saw over here in the shard manager, right? We have a vector of local shard tasks. These shard tasks are kind of single task, and they're kind of, and you remember from the task tree. Let's refresh our type hierarchy here. I know I've got the task tree in here somewhere, I think. Is it the right one? Nope. I thought I had one for the task types. Maybe not. Maybe I've lost the slide that had the types. But effectively, a single task is a kind of point task, or I guess I shouldn't really say it is a single task, right? And the other kinds of single tasks are, just to refresh everybody's memory, right? We've got individual tasks and point tasks, which we've looked at before, right? And then we've also got our shard task. So it's the third kind of single task. And a shard task is really simple. It actually doesn't know about logical analysis or anything like that. It actually, most of the stages of the pipeline are actually going to be no ops. The thing it does is it sort of is a placeholder. Where's our picture here? It's kind of a placeholder for having a parent, for representing this particular control replicated task on this local node here, right? For this particular shard. Right, so effectively, you need to have every context needs to have a owner task. So you need to have sort of a placeholder one on this local node to represent this particular, control replicated task. And so the shard task effectively acts like that. It's the owner of this replicated context. You can actually see that. I think its inner context, its context is actually going to be one of these replicated contexts. Right, and so each shard task, right, will then have an inner context, right? Like effectively, we jump to Legion context.h. That's runtime. Here we go. Right, you need to have an inner context, right, for every task that's going to potentially be running and launching subtasks, right? And of course, the one for this one is a replicated context, which is a kind of inner context here. Right, so effectively, this replicated context is going to be, a special kind of inner context that overloads, the inner context interface, and then handles all the callbacks for things like launching subtasks and other things in a control replicated context. And I think we've looked at this before, but just to tie this all together, right? Replicated context knows that it's going to be creating shards or that it's part of a bigger control replicated task. And therefore, it has to do things to cooperate with the other replicated contexts when launching tasks and things like that, right? And all the operations that get made in replicated context, like subtasks and other kinds of operations, they're all going to be the replicated versions and not the normal kinds of operations like inline mappings and attaches and detaches and stuff like that. Right, so effectively you get a replicated context associated with every one of the different shards that the user has asked you to make on each of the different nodes. Right, and this is effectively how we start up control application, right? Like effectively we'll make these shard managers. Each of these shard managers will make a shard task and a corresponding replicated context. And once they've all created themselves, then you can actually start running each of the copies of these replicated contexts on the appropriate processor, right? And that kicks off the shards for actually doing the execution for control application. Right, and then just to tie all this together, let's actually take a look, just to make it very clear what is happening. Right, so if we actually looked at replicated context, execute index space, right? So this is the this is the index-based execution for replicated context, right? And the thing that's different is that it'll actually make a REPL index-based task launch instead of a normal index-based task launch, right? And then kick that off into the process, right? So the fact that you've got these replicated contexts is what guarantees that you get, replicated execution of operations like index-based task launches and stuff like that. And so that's kind of how we bootstrap control application, and these are the important data structures that are going to manage the execution of control application and kick off the right kinds of subtasks. Any questions about that before I move on? Okay, no questions. All right, great. Okay, so effectively, this is the framework in which control application actually exists, right? And the important thing to realize is that, whenever you need to, whenever an operation, say, executing one shard needs to potentially talk to an operation in a different shard, right, it actually knows how to go navigate these particular data structures to figure out, where this other shard exists, right? So if, shard 0 needed to send a message to shard 3, right, there's actually a way for an operation executing shard 0 need to send a message to the corresponding operation in shard 3, right? There's a way to effectively go talk to the replicated context, which can then go talk to the shard manager, figure out that shard 3 is actually on node 2, which sends a message to the shard manager on node 2, right? Which then finds the local shard 3 on that node, and then finds the corresponding operation and talks to it over there. And so there's infrastructure for effectively providing or for doing communication, where necessary between different shards, on these different nodes. I'm not going to go into that whole lot of detail right now because it's a little complicated and it varies a little bit depending on the kind of message you need to send. But it's important to realize that there is infrastructure for doing that, and there is ways to know, given that you're on a shard and on some particular node, how to get to a shard on a different node if necessary. And maybe the shard is actually on the same node, and therefore you can just indirect through your shard manager and get there right away without ever actually having to send any messages. That's possible too. Okay, so let's see. I guess the next thing that I want to talk about is effectively sort of an important concept in control application, which is we've kind of been using a lot of examples of index-based task launches going through the logical dependence analysis stage of the pipeline. Where'd that slide go? Right, and they're all this stage of the pipeline is completely replicated across the shards, right? They're all doing exactly the same logical dependence analysis, across all the shards to figure out where fences go and stuff like that. And we've kind of been assuming that then once you get to the physical mapping analysis, right, that each of the we actually call the select sharding functor mapper call here, right? Right. So for tasks, there's a way to select the sharding functor, and that functor will effectively allow the runtime to say, for when you actually do the physical analysis, which shards or which point tasks in this index-based task launch are going to be assigned to our local shard, right? Effectively, you can pick a sharding functor, and then that sharding functor can say, points, 1 in 8 or something are assigned to the local shard. The local shard, right, and therefore they should be run through the mapping analysis stage of the pipeline on this particular node, right, or on this particular shard, right, and that's a way of completely sharding, say, an index-based task launch, right? So, when they get the mapping analysis, each one of the point tasks in the index-based task launch gets assigned to exactly one shard to perform the physical analysis, and do their mapping, and then they can start running, right? And that's a perfectly reasonable thing to do. And so what that actually exists on this end of the spectrum of potential transitions between sharded and replicated. And we're going to look at some examples of things that are replicated in control applicated contexts here in just a minute. But effectively, it's when control application started, everything was fully sharded, right? Meaning that every operation, every point tasks and stuff were assigned to exactly one shard to actually run and do all of their analysis and make that work, right? But there are some operations for which that's actually not possible, right? So for index-based task launches, you can always fully shard them, right, and assign exactly one point task to every shard for mapping and analysis. But for some operations, that you can't actually do that. They actually need to be either fully or partially replicated and partially sharded, or maybe even fully replicated. So let's actually take a look at an example of one of those particular operations. So it's actually let's see, where is Legion replication? Oh, here it is. So this is a very common operation that needs to be fully replicated in a control-replicated context, right? And that is a inline mapping operation, right? So effectively, sometimes the user wants to actually make a copy of like a logical region in the parent task, right? And they need to inline map that and be able to access that, right? So we've got this the way they do that is with a map op, right? And that map op is a very standard kind of thing, but in control-replicated contexts, they actually are a little more tricky, right? So if we go back to our picture over here, right, imagine that each of the shards all want to map like the same logical region for, let's say, read-write privileges, so they can mutate it locally inline in their parent in the parent task, right? Well, that's going to be very tricky. You can't actually shard that because like every one of these shards needs to have their own copy of the logical region data that they're all going to mutate. Now it's control-replicated, so they should all be mutating the data in the same way. But you can't shard it. You can't just say that like one of these shards is actually going to be the one to actually mutate the data inside of a physical instance, right? You need to actually replicate it to make sure that every one of these shards that's executing the task can actually get its own copy of the data to be able to read and write and stuff like that, right? And so that actually falls on this fully replicated end of the spectrum, right? We're actually going to have to map this inline mapping operation on every one of these shards, and they're all going to have to map to the same logical region, right? And create their own physical instance and bring it up to date, and then be able to mutate it themselves, right? And so what that means is that like in the mapping stage of the pipeline, each of these REPL map ops, where'd they go? Here they are. Are going to have to be able to do their own mapping and cooperate to create their own copies of the data. This is a little tricky though. In fact, it's not entirely obvious, what the semantics of this are if like your inline mapping operation has read-write privileges on the logical region, because now each of the shards are actually going to be able to read and write the same logical region at the same time, right? Which is kind of racy, right? Like it kind of like makes it look like there's some races associated with that process, right? And so when a REPL map op goes through the pipeline and gets to the mapping analysis stage of the pipeline, we actually enforce just one invariant really, which is that if they're going to be reading and writing, they have read-write privileges on the logical region, we're going to guarantee that they each map to a different physical instance. So shard 0 will map to one instance, and shard 1 will map to a different instance, shard 2 will map to a different instance, and so forth. And then what we do is we actually do a collective mapping of these processes, right? So you can actually see some of the mixin classes here in this class for REPL map ops, right? You can see they're instances of collective view creators, right? And this collective view creation, we haven't talked a lot about collective view creation or analysis, but effectively what's going to allow these mapping operations to do is to actually map the different copies of a logical region at the same time. Now, commonly this is used for like collective behaviors like all reduces and read broadcasts and stuff like that. But it actually works here for these control-replicated REPL map ops also. It effectively allows the runtime to do the analysis collectively for the same logical region across all of the REPL map ops on each of the shards. And so they can each map to, map a different copy of a logical region, collectively together at the same time. And then they can each, then once the mapping is done, they can each shard can read and write, that their copy of it locally, and we're done there. They can unmap their operations and so forth. So that's an important, distinction between like when an index-based task goes through the mapping stage of the pipeline where it just shards, and each shard has its own set of points that it's handling this disjoint from all the points, and other shards. In the case of some operations, like inline mappings, but also in the cases of things like attach and detach operations, we actually are on the like fully replicated side of the spectrum where, all the shards are actually doing exactly the same thing and doing it collectively together. Now, in between this, like while we have these two extremes, like the fully sharded for index-based task launches and fully replicated for things like inline mappings and attaches and detaches and stuff like that, we can also have cases where like there's like partially sharded and partially replicated. And what I mean by that is like some of the shards will be, doing the same operation collectively, and some of the shards will actually be doing very distinct things, right, inside of our case. I'll give you just one example of this because really I think there's only one very common example in control application today, which are index-based attach operations, which often fall in this like partially sharded and partially replicated sort of mode where effectively like some of the point tasks are all mapping the same logical region for like the same file on different nodes, right? And that's the partially replicated part. But then some point attach operations are actually doing like attaches for completely different files, right? On potentially the same node, right? And so therefore you get this weird mix of only some of the point tasks inside of like an replicated index-based attach launch are cooperating with each other, but not all of them are cooperating with each other. But it's useful to keep this sort of spectrum in your head, right? Like when you're doing a control-replicated execution like this, when each of these shards are executing or launching subtasks or sub-operations and stuff like that, sometimes those sub-operations are fully sharded, sometimes those operations are fully replicated, and sometimes they fall in the middle, where they're partially sharded and partially replicated. And they each go through the pipeline, and do their mapping stage accordingly based on, how they're actually doing this. Right. So anyway, that's an important detail of control application that I think is useful to keep in mind, right? Like effectively, you have to have this different operations go through the pipeline in different ways, especially when they get to their mapping stage of the pipeline. Again, none of this applies to the logical analysis stage. In the logical analysis stage, everything is replicated and all shards are doing exactly the same thing. But when you get to the mapping stage, then things sort of bifurcate. Right, and you can get different modes that operations can go through the mapping and later stages of the pipeline based on those things. Okay, any questions about that? I didn't do a whole lot of detail on these, but because like I think what will happen is we'll actually start to look at probably wait for folks to look at particular operations inside of going through the pipeline and then realize like, oh, this is what fully replicated means, this is what fully sharded means, this is what partially sharded and partially replicated means. And when we do, we can dive into those details, or dive into those that part of the code in a little more detail. But it's important to keep these ideas in mind. Any questions on that?
I guess I would want to understand an example of fully replicated case better.
Fully replicated. So what didn't make sense about the replicated mapping operation? Can you ask?
So I wanted to maybe there are operations, but having parallel read and write operation on the same logical region, I wanted to understand like in which cases we want to do that.
So Lead actually has a fair number of use cases of this. So often in the case like they will often sometimes they need to hand back they need to switch back to normal Python execution of like a NumPy operation that they haven't handled yet. So they do an inline mapping of like a NumPy array, right? So that they can call normal NumPy instead of like calling Kunumeric's version of a NumPy operation. In order to get the most recent version of the data for that, that NumPy array, if it's a Kunumeric array, right, it's been backed by a logical region, right? And so they need to get the most recent copy of the data so that then they can call the NumPy version of that, right? And if
right. But what is the definition of a recent version if like I get 5 parallel tasks simultaneously reading and writing?
Yeah, well, imagine you've got a NumPy program. It's running along, kicking off NumPy operations, right? Most of which are accelerated by Kunumeric, right? And so they're all deferred and asynchronous and stuff like that, right? And then you come to a NumPy operation that Kunumeric hasn't implemented yet, right?
Right.
You need to actually like stop, wait for all the Kunumeric execution to finish. Inline map the logical region that the Kunumeric array that you need to operate on is being backed by. And then you can call the normal Python or the normal NumPy version of the function, right?
Right.
So you need to kind of like wait for the asynchronous deferred execution to finish, right? Then you can, that's what your inline mapping is going to do, right? And get you the most recent copy of the data, right, from all the prior Kunumeric tasks that have been launched, right?
So the tasks that have already been launched, those are the fully replicated tasks. That's what you're saying?
Well, most likely those tasks are sharded, right?
Sure. Right. Right.
Right, like you're executing normal index-based task launches for numeric accelerated tasks, right? And they're all getting sharded and executed and stuff like that across the various different shards,
Mm-hmm.
right? But then you
Right.
come
Right.
to
So
an
those are like, divided. So that makes sense to me, right? They're
yeah,
not working on the same data.
yep.
So sure, they can, they're sharded.
Well, they're sharded, but they're operating on different subsets of data, right? Like often when you shard something,
Subsets of data.
right,
Exactly.
you're each of the point
Disjoint,
tasks
right? They're
are
disjoint.
using a different subregion in a partition, right?
Mm-hmm. Mm-hmm.
Right.
Mm-hmm.
And so like that data is
Yeah.
actually partitioned and sharded and distributed and all sorts of
Yeah.
stuff, right?
Yeah, that makes sense to me. Yeah, that makes sense to me. I was just trying to understand when you working on the same logical region, right?
Right. But then like if the shards come to a Python operation or sorry, a NumPy operation that they haven't
Mm-hmm.
accelerated with QNumeric yet, the way QNumeric implements
Mm-hmm.
that is they do an inline mapping because they need to wait for all
Mm-hmm.
the
Right.
they need a copy of that logical region's data, with all the prior tasks having finished executing, right? And they need the
Mm-hmm.
same copy on all the shards, right? Because all the shards are going to call the same base NumPy version of the class of the function, right? Um,
So all the shards are going to compute the same thing.
all the shards are going to compute the same thing because you're doing it inline in the parent task, right? Because
Right.
haven't implemented this in QNumeric yet, so you haven't actually made it.
Right. Right. So is the reason because then we want to again like use qnumeric maybe later down the
And then
path?
you use it later, but you effectively don't want to die on a NumPy
No, no,
operation
no,
that
of
you
course
haven't
not.
implemented,
That makes sense.
right?
That makes sense. Okay, okay, okay. That makes sense.
Yeah.
Okay, okay, yeah,
And
yeah,
so, I
yeah,
mean, that's
sure.
actually a good example. Like, the execution is almost like it's fully sharded, for most of the QNumeric accelerated part.
Mm-hmm.
Then it has to swap back to fully replicated for the part where you have to call out to NumPy, to do the operation you have
Mm-hmm.
implemented
Mm-hmm.
inside directly inline in the parent tasks, right? And then you can switch back to a sharded mode, right?
Right, right, right. Yeah, that makes sense. That makes sense. Yeah.
Yep.
So it sounds good. Yeah, that's a good example. Okay.
Yep. So that's a very common case. In fact, like this was actually buggy for quite a long time in control application, and I'd say maybe about like with the coming of collective views, sort of were the magic thing that made it possible for us to do this in a sane way,
Mm-hmm.
and to do the fully replicated part of this execution has made it much more stable and correct all the time. Whereas before, the way we were implementing replicated map ops before was not it was kind of hairy and very ad hoc and not very disciplined. So
Mm-hmm.
yeah, but we have this mode now where you can switch back and forth between. You can do these replicated map ops correctly and switch to fully replicated mode where each of the shards are executing the same thing on like the same logical region with rewrite privileges.
Mm-hmm.
There are some checks. This is one area where like there are some weird mapper invariants, right? Like for read write inline mapping operations and control replicated tasks, we actually enforce that the mapper have mapped each of the copies for every shard to a different physical instance of that logical region because
Right.
right, like you could have two shards on the same node potentially like using the same instance. That would be bad because they're both reading and writing at the same time, right?
Mm-hmm.
By forcing them each to map to a different instance, then you get isolation, so you don't have to worry about races. And we trust that this is a control replicated task, and therefore those reads and writes at the end of the day, when all the shards are done doing their reads and writes to the replicated inline map version, the data inside of each of those instances is exactly identical with each other,
Correct.
right? Like,
Correct. Yeah, yeah.
yeah, and we kind of assume that, right? Like we don't actually check that, but we assume that's a property of like control application that's actually safe to allow replicated map operations with rewrite privileges for exactly that reason, right?
Mm-hmm.
Yep.
Makes sense. Makes sense.
Yep.
Okay.
Yep. So just something to watch out for. Watch out for there.
Mm-hmm.
Yep.
Mm-hmm. That's good.
Okay. So the last topic I wanted to talk about today was just one other sort of like data structure that that shows up in control application, which maybe some folks which we haven't really talked a lot about previously, but is an important one for just closing the loop on control application. And that is let's see, where is my runtime.h class? And that is how do we deal with futures in control applicated contexts? So effectively, in previous Legion lectures, we've talked about future maps, which are effectively, if you do like an index-based task launch or something like that, right? You can effectively create a future map, right? Of that represents the all the futures for like an index-based task launch that have come back to you, right? But if you do a index-based task launch in a control-replicated context, right? Well, then we need a special kind of feature map, one that knows, that we've only going to get some of the features on this shard, and maybe some of the features are going to live on other shards. And so we actually have like a replicated feature map class that extends the base feature map class. Now, these are the impls, right? So these are not user-facing, right? Effectively, for the user, the interface for feature maps are exactly the same. They can ask for features and be able to get the names of features from that were produced on other shards, and everything just works. Like the interface is exactly the same. But internally, effectively the way that we handle that is we have sort of a replicated version of a feature map, right? That effectively knows that this is a feature map that exists in a control-replicated context. And if you ask for like a feature, right, you may need to do some additional work to actually go find that feature. And so I figured we actually take a look at how that actually works. Where did my runtime.cc go? Maybe I did not open it. Let's see. So if we look at REPL feature map impl, get feature. This part, the beginning part, is actually very similar to the non-control replicated case. If we've already got the feature, great, we're done, right? We look it up in our local map of features. But if we don't have have the feature locally, right? We need to actually go find that feature from some other shard, right? Most likely it was produced on a different shard than our own, right? And the way that we do that is we actually need to use the sharding functor to help us out with this, right? And so feature maps will, one interesting thing is like when you launch the index-based task launch, you may send off this feature. You have to return the feature map right away asynchronously to the user, and so you may not have picked the sharding functor associated with this feature map quite yet, because like the index-based task that is running through the pipeline picks its sharding function down the pipeline a little bit, a few stages down, right? And so we may have given this feature map back to the user right away. So we might need to wait, to be told what the sharding function is for this particular feature map, right? And so we have a little wait here just in case that's or we detect if we haven't gotten our feature map or gotten our sharding function set yet. But eventually, like the index-based task launcher operation will eventually tell this feature map impl, what the sharding functor was for this that made this for the index-based task that made this feature map, right? And then we'll be able to resume from this. And once we do, we can actually find, we can use that sharding function to find the owner shard for a particular point feature that the user has asked for this feature map, right? So effectively, we can actually get the sharding function and invoke the shard function, right, to find the owner for this particular point, right? So we pass in like the domain of the of this feature map, and we pass in the point that the user is asking for, and this will give us back the shard that actually owns that, right? And then, after we've done that, we can now ask the shard manager on the local node, who actually, which address space actually, which node does this is actually going to produce this particular shard feature, right? So we can ask it to get the shard space, right? Effectively, which address space, which node, right? Actually, is going to or has that particular owner shard. And once we've got that, then we can actually send a message to that node to actually request, the feature the same as we would, for requesting a remote feature, on a normal feature map, right? And we can get the resulting feature and populate it, right? And of course, like if we're the owner node, then we can actually go make our feature locally. It'll get filled in eventually, and so forth. That's kind of the same as a normal feature map, but there is this extra logic here in replicated feature maps that actually allow you to figure out, to use the sharding functor to actually figure out, which node is actually going to be producing a particular feature if you're not the local, the producer in a control replicated case, right? And just come back to this picture, like, maybe shard 1 is asking for a feature that's not local, right? And so it figures out that like shard 5 is the one that's going to produce that. It'll figure out, effectively knows how to look, realize that shard 5 exists on node 3 and then send the message to node 3 to actually get that remote feature and send it back over here to us on shard 1, right? And so that's an important property of feature maps, is that we do have these replicated versions of feature map impls to handle the creation of or handle getting features and stuff in control replicated contexts. this actually does remind me of one other thing I do want to talk about. But are there any questions about that before I go talk about something else about feature maps?
Not about that, but I want to understand how we wait.
How we wait. Go ahead. Ask a question. Let me go back to the code. Yep. Is that like this part right here?
I mean, I wanted to understand like how we wait on a remote future.
Oh, you mean like in the application or inside of Legion?
Yeah, maybe an application because I did reductions on, and it was nice for me. I wanted to understand like how this distributed future thing works.
Ah, um, so maybe that might be a slightly bigger topic, but let me take a stab. Let me take a stab at it right now. So futures right in Legion are, they're represented. They're a future object. Represents data that will eventually be filled in. Usually it's like return values of tasks and stuff, right? So like.
Mhm.
Right, so eventually, like when the points in index-based task launch finish, right, they populate their future with the return value of their task, right, if there is one, right, that effectively says that that point task is here's the value that was produced by that point task, right.
So internally, I guess we just wait and to get a signal from the remote. I mean, the other shard
Exactly,
tell
but
us when the task is done and what the result is.
yes, but I would say like we kind of discourage waiting on futures. Usually, the better thing to do, right, with futures is actually, since we got it here. Right, like usually what you do is like when you launch another task, you can add a feature as a dependence to that task. And like
Right. I
that's
mean, of course, like have I think, launch more things and then wait for the result at the end. Of course.
right. That's the preferred way, but they're effectively the future class does allow you to wait like in the parent task, right, for future results, right? So like futures do have a get result method. They've got a get void if the is a void type. We also support the C++ feature interface, right? Like here's a get valid and wait, which I think come from like the C++ feature interface. So like you could pass in a Legion feature as a template argument to anywhere that like took a feature interface argument for C++, right? So you can wait in the parent task for a feature to be valid if you really want to. And if that's the case, like, that'll actually go get, that'll actually wait on, the result being populated inside of the feature. But like, the interesting thing here is like, this is actually like a step before that, right? Because this is like the, how do you get the name of the feature from the feature map, right? Legion has this concept of feature maps that don't really exist in other, at least I haven't seen them in other feature systems where like, effectively it's a group of features, right? And you maybe want to extract one feature from that feature map, right?
Right.
Right, and so like the feature map class, right, effectively has is effectively a group of features, right? And then you can extract, particular features associated with a particular point in the index-based task launch, right, if you want to. But you can also pass in a feature map as an argument, like an index-based task launch, right? And then have individual point tasks grab other points from those from prior index-based task launches through the feature map. So.
Yeah.
Okay. All right. Let's see. So we've got this other way of getting, where'd it go? Effectively getting features in control applicated contexts where we actually have to look up which shard is going to actually produce that feature, and then which address space that shard lives on, and then we can go actually send the message to actually go get the feature associated with that particular replicated feature map. So a little bit of an extra level of indirection for replicated feature maps that exist. I do want to make one more point here about features in the Legion API. Oh, did I? Let's see. Oh yes, here we go. See if I can remember the name of this method. So there's effectively just like one place. So normally, in addition to like index-based task launches and stuff that create feature maps, right? We also have these construct feature map API calls, right? There's a few of them here. Various kinds of construct feature maps. I guess there's just the two here, right? For passing in either like a set of values, like a set of points and untyped buffers, right, to create a feature map in line in like a parent task, right? Or you can effectively construct one manually from a set of points and features that you've already created some other way, right? Now this is like in general, like with control application, we want all the code for each of the shards to be exactly the same. But sometimes when you're actually dealing with creating like if you're getting data from like outside of a Legion application, you might need to construct a feature map in a way that each of the shards are producing some subset of the data, right? And not have each shard produce all of the data to make it to completely abide with control application. And so this is like the one and only place where we allow, an API call that actually doesn't have to produce the same. It doesn't have to produce exactly the same args across all the different or arguments across all the different shards, right? So normally in control application, you're supposed to call into Legion runtime, with the same arguments on each of the shards. We should be able to check that all of those values are exactly the same across all the shards that are passed into Legion, right? And there is a way to not do this for this construct feature map call, right? There's effectively this collective argument here, right, which effectively says whether or not all the shards are collectively creating this sharding or this feature map, or whether they are each producing, a subset of the data, right? Right, and so by default it's false, and that sort of conforms with the normal way of doing Legion, which means that like each of the this map of domain points on type buffers should be the same across all the shards, and each of the shards are providing exactly the same data structure here. But there is this, if you set this flag to true, you can actually construct a feature map in a way that allows each of the shards to pass in a subset of the data, right? So that means that this data structure, this data here, right, you can have some points assigned on some shards and some points assigned on other shards. And that will actually, create a replicated feature map in a way that, allows you to actually construct a feature map with each of the shards providing only some of the input data. And that works on both of these two methods, right? Effectively, this collective argument is in both cases, and you can effectively pass in, different data structures, and if you set collective equals true, right? And that allows for effectively cases where each of the shards want to pass in a subset of the data. This is like one of the few places that I allow for this property of control application to become visible through the API. In fact, I think it's the only one other than like explicitly asking for your shard ID, because like this is an important enough use case where users actually want to make replicated feature maps, right, themselves without having to use an index-based task launch to do things all the time. So something interesting to keep in mind, and if you set collective equals true, right, you'll actually get a replicated feature map behind the scenes inside of the Legion runtime. Any questions about that?
Would we go through the same get feature function in the case of collective?
Yeah, if you set collective equals true, then what gets made behind the scenes is a replicated feature map, right, that effectively allows for you to be able to look up features to actually be able to do that. And actually that's a good point, because like if you do set collective equals true here, we do kind of ask you, if possible, to tell us about the sharding ID that actually produces the mapping of points to shards that you're providing here, right? You can, because like effectively if you do set collective equals true, right, each domain point inside of this index space domain should exist in exactly one of the shards, right? So like each shard should set the domain point with an untyped buffer on, or exactly one shard should provide, an untyped buffer for each of the domain points in this index space. And we'd like to know the name of a sharding function that actually does that if you've got one, right? Like effectively we would prefer that you tell us about this, right? Because like then we can know the sharding function for this replicated feature map. But if you don't know it, or if it's like kind of just an implicit mapping that's like not obvious what the mapping is, you can set this implicit sharding equals true, right? And then the runtime will actually like kind of create a feature map, create a sharding function that will, represent this particular mapping of, domain points to shards to actually handle that for you, right? And that's why all these are like, there's a whole bunch of like optional options here, or default options for the control applicated cases where collective equals true. Most of these arguments are like most of these arguments in a non-control applicated context are just meaningless. They're not even checked or used or anything like that, right? But in the case where, you are creating a feature map from a set of like in a collective way, we would like you to tell us a sharding function, but if you don't tell us, then we'll still be able to make a sharding function for you behind the scenes. It'll be a little more expensive to do that, but we will do it. And that way, this replicated feature map actually does get a it'll like effectively every replicated feature map will eventually get a sharding function that'll get set in one way or another.
Makes sense.
Yep, that was a good question, because like that's why some of these arguments exist on these particular construct feature map API calls. And effectively, we say if you're going to do the slightly unusual case of setting collect equals true, then we'd like you to tell us a sharding function, but if you don't, then we'll do it some additional work to construct an implicit sharding function for you. So, yep.
Yeah.
Okay. Anything else for any other questions about control application? That was all the topics that I had for today, I think.
I think this is good for one day.
Okay. All right. Well, next time we'll see what topics come up. But I'll call this one miscellaneous control application topics. Yeah.
Yeah.
All right.
Sounds, yeah, got it.